They told me that I couldn't have a wireless mic up here because apparently they're afraid I'm going to hack it. I don't understand. You know that you're at a very interesting conference when you walk around and Bluetooth pops up. See, I've got a Bluetooth tool that just pops up everything that it runs into. It's almost like a denial of service sometimes. You know that you're at an interesting conference when you get names like White Witch or, oh, here's a good one, Nut Cheese. And yet I'm still amazed at the sheer numbers of people who forget to turn off their Bluetooth at Defcon. But that's not why you came to hear me today. But I'm giving people a little bit of time to walk in. Hello, my name is Atlas. I like what I do, and I do a lot of it. A while back, I'm in a subway in D.C. with a friend of mine. And I forgot to ask his permission, so I can't say who it was. But this friend is very well known by most of you, I guarantee it. And he's the cream of the crop in security and in the hacker arena. Well, anyway, this guy is talking to me, and he says, Atlas, explain to me how buffer overflows work, because I'm just a little fuzzy. I've read a little bit about it, but I just don't have it. And I told him an answer, but I thought to myself, if this guy needs a refresher course on heap buffer overflows, I think I should probably... I thought they were going to provide me music. I said, hey, there's probably a lot of other people out there that don't quite remember how they work or just never knew, and that's cool too. They're actually kind of esoteric. Clicker.
Bluetooth?
No! Great. Gotta love that. Wow, this could be very interesting. There we go. It works again. So this is Remedial Heap Buffer Overflows. Basically that means I understand most of you guys are lead enough to have done this before or at least broached the subject before. So this is for you. This is a talk about how to exploit buffer overflow vulnerabilities, specifically with a heap and a DL malloc heap structure in place. We don't have a lot of time. Sorry about that. In the man page for the getS function, there is an exceptional note. It says, never use getS. Because it is impossible to tell without knowing the data in advance how many characters getS will read. Basically, don't use getS because we're in C now. In C, you have to tell it, much like assembly. This is how much room I want to give you. And getS just says, whoo, starting point, let's just race. Da-na-na-na-na-na, looking for a zero, da-da. And you hope that it's still within your buffer. But if it's not, who cares? You get a little crash. Not a big deal. fgetS also has some issues. It is a step up from getS. There's a ton of C functions that give you all sorts of beautiful, scary functionality. But the big ones are string copy, mem copy, scanf, or the scanf series of or family of functions. One that a lot of people overlook is actually not a function in C at all. It's an assembly thing. In fact, it is the glue that makes all these functions work, and it is the moveS assembly opcode. Anybody heard of that? Yep, a lot of you. So moveS takes a parameter or a prefix, says repeat. Hey, repeat this many times, just move from here to here. That's pretty cool. How many of you are programmers or have written C programs or Python programs or any other language? Thank you. Excellent. Big, a large amount of you. You guys get to watch me walk up in front of the table because of the whole wireless thing. So if I fall off, please try to leave my badge alone and my wallet. You can take... Okay, no, I'm not going to give you permission either. When you're programming, what do you use to store information? You use a variable, right? Right? There are two types of variables in a C program. There are local variables, and those get stored on the stack. There are also dynamically allocated variables. In other words, I don't know at the time of writing how much data I'm going to need. So we set aside a huge chunk of virtual memory space and allow for a heap. Now, a heap is a very low-level function, but it is not operating system specific. We'll get into that in just a second. The heap is dynamically allocated storage at whatever size you need, and it can be very fun to secure. Who's heard of a stack-based buffer overflow before? In fact, who's heard of a buffer overflow at all? Show of hands. Excellent. How many of you know what it means? Thank you. Excellent. Good. Stack-based buffer overflows are beautiful. You start at one location and you meander. Oh, that byte needs to be right there, so you replace it very nicely for the program so it doesn't crash. Keep going, and you overwrite something of very big value. Oftentimes, this is the return pointer for your function. Heap, however, doesn't have the return pointer of the function stored in the heap. So what can I do? How do I take over a computer system using a heap buffer overflow? Well, before we get to that, I'd like to back up and say overflowing a buffer is valuable. Let me hear it, everybody. Yeah. Overflowing a buffer is valuable. Why is that?
Stop a process without erasing anything, lock the system up, go back in later, and see exactly what's happening and stop.
Wow. Yes. Can I summarize? Because I don't remember everything you said. It was really good. But basically, there are several reasons that buffer overflows are great. You can stop an entire machine, or at least a process, from running. Denial of service. There are several other ways that you can exploit, not meaning shellcode necessarily, but exploit a computer program because of a buffer overflow. First of all, you can overwrite other variables on the heap. So, for instance, if your program has in it members of this group stored in this heap variable have administrative access to my tool, and you happen to buffer overflow just before that, well, you can go, oh yeah, hey, that's my group, Atlas group. Suddenly you have administrative access. You can control things you should have no business controlling. Another interesting one that's often overlooked is the ability to take a string variable, for instance, get rid of that nasty little null at the end that keeps the printf from printing more beyond that point. And instead of overwriting, you can now, with the help of a printf that very likely already exists for you, get access to read whatever comes after your buffer. So that we'll call that end of string overwrites. You're overwriting the null at the end of your string. But of course, the creme de la creme, the most exciting, this is going to kill me. Hold on a second. The most exciting thing that we talk about when talking about heap buffer overflows is tinkering with in-band information. In-band management information, to be exact. It's a delicate process, and it's one that's not very well understood. So a little bit more about heap memory in particular, generically speaking. A heap is a chunk of information that is given to a process by the kernel. If the process needs more, it goes back and has a very brute force request to the kernel, hey, I need more space. Can I have more space, please? And the kernel will say, yeah, here's a couple gig. Okay, maybe a couple meg or whatever. It's up to the program to then decide how to manage that information. How many of you have a bedroom at home? How many of you have a clean bedroom at home? Get out of here. I don't want you in my room. Why is that? Well, because many of us understand, whether we're good at it or not, we understand that open space requires management. So, DL-malloc is an implementation of a heap management system. It was written by a guy named Doug Lee, thus the DL part. Somebody asked me about that earlier. I forget what he said, but it was really funny. Yeah, sorry, sharing my internal jokes. So Doug Lee wrote this heap management system, and he made one mistake, or maybe it was intentional. I'm not beyond guessing that. And in my line of work, I like to think along those lines. I think the people who wrote the stack, I think they were just really evil. Because who else would say, hey, start here and keep writing over the return pointer? Doug Lee and several other heap implementations, they make use of what's called in-band management data. In other words, my chunk is 101 bytes long. Do some math, make it round off so that it's stack aligned and all that beautiful stuff, or aligned in some way. At the very beginning, just before what you see when you get a heap variable, the 4 bytes leading up to your memory space are actually a counter that says, hey, anybody looking at me, the next heap is X number of bytes ahead of me. Okay, so heap buffer overflow. Boom, dum, dum, dum. Wait a minute. I want to change that one. We'll get there. In this presentation, I use the words chunk and buffer fairly interchangeably. Understand that when you're talking to somebody who hacks around in kernel space all the time, which I don't, I spend some time there, I enjoy it, but they will say, no, what the kernel gives you is a chunk, you're talking about a buffer. But I will use them both, so please don't get lost in that. It worked. So for example, we make a call to malloc. This is the Doug Lee malloc, or yeah, this is the call basically that says, I need this many bytes. And this can be a variable. That's what's so cool about heap. So we're going to say, I want something at least 1024 in size, because that's what I'm going to use of it. I don't really care if it's 1048, as long as it doesn't eat up too much memory space. So malloc goes out, says, based on these rules, I'm going to cut a chunk and give you a pointer 4 bytes into the chunk, because we have our management stuff there. One thing that's important to note is that malloc and its counterpart, free, are called so frequently that most sanity checking that you'll probably think during this presentation, why don't they just check? Most sanity checking costs too much. If you take something that's iterated thousands of times during the boot of an operating system, for example, and you add a second here, even a half a second, over time, Vista doesn't boot very fast. Then again, over time, Vista doesn't boot very fast anyway, so I guess that doesn't matter, does it? But in the Linux world, we see that not much has been done to correct this. Some stuff has. The important part when dealing with this type of heap buffer overflow exploitation is the function called free. If we fill up a buffer and overwrite the next buffer's management information, the The thing that's going to make use of that, however, is a call to free. So you've got two buffers. The second buffer has management information just past your buffer. You overwrite that, you call free, and free reads that information and makes decisions based on what you've written there. That slide seems out of place, doesn't it? But I'm going to say it anyway, because back in 2004, a vulnerability was found in a Microsoft core library in the parsing of JPEG files. You guys remember the GDI buffer overflow? Do you guys remember that it took third-party person to release a tool to even help you figure out if you're vulnerable? Because everything uses this thing. Anyway, he's a good friend of mine, Tom Liston. I had to give him a shout-out. So he wrote this tool. He works for Intel Guardians. Good bunch of guys, good friends of mine. The problem with learning heap buffer overflows, and the reason that it's not nearly as focused on as stack-based buffer overflows, is that stack-based buffer overflows are fairly consistent between platforms, at least among the same hardware. So you've got BSD, you've got Linux, you've got Windows, and Windows, and Windows, and every other version of Windows. There are several implementations of a malloc system. Doug Lee, I enjoy his very much. RTL is what they call it in Windows. The BSD PHK implementation, I hate this one. There is no in-band management, and I'm having to hack a binary doing this right now. In fact, you guys have been down to CTF, right? After this, I will be running down there because my team is still in a heated struggle for first place. And you guys should all come down and check it out. It's really cool. This is what good guys do to go be evil. There are also several other implementations. System 5 has their version. BSD for AI, I'm sorry. Yeah, BSD and AIX have some, did I say BDS? That means something completely different. What's most important isn't what happens when we allocate a buffer with the Doug Lee malloc. What's really important is what happens that we never see. You see, after you free a buffer, malloc says, or Doug Lee says, they don't need that information anymore. So you know what? I'm going to use some of it. Before, we said, this guy right here, just before the buffer, is going to say how many bytes to the next buffer. However, when we free it, we're going to use several more chunks of information, or chunks of memory, to store more information. Because when you write a program, you're using a heap. Your heap chunk, you maintain that. You manage it. You have pointers to it that last throughout your program. But when you return it back, you just say, I don't need that anymore. Doug Lee then has to take care of it. So the Doug Lee malloc sticks these buffers that are unused into a doubly linked list. Anybody know what a doubly linked list is? They were kind of a pain to do back in college, but they come in very handy. So Doug Lee stuck all these suckers back into a doubly linked list. And the particular exploit that we're going to talk about today has to do with this doubly linked list. Specifically, what do you do when you have two buffers that are freed in this doubly linked list? I don't know. Well, you just leave them alone, right? They point to each other. You're cool? Because on your hard drive, what happens when you've got chunks of data spread all over your hard drive? It gets slower than Vista. Did I say that? Yes, it slows down because the operating system is having to tell the hard drive, go here, go here, go here, go here, go here, go here, go here. Malloc, or heap implementations also have to deal with the same thing, fragmentation. So when you get two free heaps next to each other, the doggone suckers, they got to be big. So we join them using a tool called unlink, and unlink is where the magic lies. So, in our example, we have a buffer. Now, I could have chosen 100 bytes or 104 bytes, and it probably would have been prettier. I chose 101 because it proves a little bit more of how this works. And I don't know about you guys, but when I had to learn this, it wasn't about reading about it. It wasn't about the theory of how it worked, because I understood that. But it was about the bits and the bytes and how it actually worked that got me to write the presentation. So if that's cool with you, I want to get into the details. 101 bytes. DL malloc then allocates truly 112 bytes. There's a little mathematics to go into there. I wrote a question for my friend G-Mark for Hacker Jeopardy that basically took this to heart, but then I pulled it out later at the request of a friend of mine who says, "Dude, they're not going to know that. They haven't seen your talk yet." So I pulled it. Anyway, the idea is, you call malloc, you say, "I need 101 bytes." You don't know that malloc needs to know that you need 4 more, or that you don't tell malloc that you need 4 more than you really need. Malloc adds that on. So you've got 105 bytes, and then, in the interest of alignment and beauty and bliss and even numbers, DL malloc then extends that to the next 8-byte boundary. What's an 8-byte boundary? Well, that's a thing in assembly no. An 8-byte boundary is, well, 8, 16. It's a multiple of 8. Nothing magic. I had to throw this slide in because a buddy of mine heard that I was giving the talk. He said, "Dude, you're not going to include Windows?" I'm not coming. So here's for you, Linux, if you came. I know I saw some of your friends, but I didn't see you. Anyway, Windows actually, and I won't spend much time here, Windows has a very similar idea of allocated buffers. You own them. You take care of them. You tend to them. When they are checked in, however, they are checked into an array of doubly linked lists. It's the biggest difference. There's some other details of how they work, and I won't get into them. I don't want to confuse you, but I had to throw it in. So we have heap buffer that we've allocated. We've stuck in my first name. Then we have another one that includes my alias, Atlas. And then I say, I don't really want to give out my first name, so I delete the first buffer and it becomes a freed buffer chunk. Malloc says, I understand that you don't need this. I'm going to take care of it. I'm going to use the first 8 bytes. How many bits is that? Yell it out. 64. 64 bits. I'm going to use the first 64 bits of your memory space. So, you've got your memory pointer to the very first byte of what you see, not the first 4 bytes, but the first byte you see. And from there, it sucks up 8 bytes to 32-bit addresses. The buffer in the linked list, it's been deallocated just before it, and the buffer that's been deallocated just after it. Got that? There are a couple other places within your buffer that it will write to. We won't get to that now. I have slides that actually explain that better. So when the memory is allocated, so notice this is used, this is kind of what the memory space looks like. We have a long integer, 32 bits. Then we have 101 characters. And then we have some padding at the end, right? Right. However, this is a bit closer to what you will see when looking at a freed buffer. I tried to find a good way to do this. I chose to do it in a struct type format. I do have something that I stole from Once Upon a Free. You guys heard of FRAC, right? I'll show that later too. I wanted to take two different approaches. But for those of you who like the struct, here it is for you. So we start out with our long. This is the length of your buffer, including all the rigmarole at the end, the padding and that. It is an even number unless the previous guy is not in use. We will say that many times. Don't worry about it. Just keep it in your head. If it's an even number, the guy before me is not in use. If it's an odd number, the guy before me is in use. So you'll look through here. You'll see the number 71 or 71 hex. Forgive me. But that doesn't mean that 71 hex later is where the next buffer starts. It really starts 70 hex later. But that just means that the guy before him is in use. Then we see two longs, the previous guy, the next guy, then the remainder of your character space, the length, again, of your buffer. I don't know why they did that. I have a feeling it was for performance sake when freeing the guy before you. But anyway, there is another copy of your length without the 1. So it's always even. And then the pad size. Everybody still with me? If you're not, raise your hand. See, that's how I get people to think that they're with, or tell me that they're with me, because nobody wants to stick up their hand. So as I mentioned, the magic happens in an area called unlink. It's actually a macro. Do you guys understand? Who here understands the difference between a macro and a function? And don't worry if you don't. Okay. In C programming, they allow you to do all sorts of things that help you as a developer think about the program, aside from secure coding. You write a function that you want to call over and over, and it becomes something in memory, its own entity in memory, that can be called from all sorts of different places. Oh yeah, from up here too. And at the end, there's a return, and hey, that return pointer that we talked about, then sends the instruction pointer back to where it came from. Most of the time. Actually, there's some fuzzy stuff there that evil people like Invisigoth from Kenshoto do that actually don't return where it's supposed to. Anyway, then you have macros. The idea behind a macro is, I want this to be exceedingly fast, so it's going to be inserted in line wherever I write this. But because I know that I will dork that up if I do it 25 times like I'm going to have to. So I write a macro, I put the macro in, the compiler says, oh, it's a macro, and I just want to make sure that that gets replaced before compiling. Also, macros are used, yes, I know macros are used for numbers that you don't want to have to call to a variable all the time. It's a performance thing. It's cool. So unlink is a macro, and the basic idea behind unlink is the guy behind me has a forward pointer, and the guy in front of me has a backward pointer. Well, I'm bowing out of this puppy, so the guy in front of me, his back pointer should really point to this guy over here. And this guy over here, the guy behind me, his forward pointer should point to the guy over here. I didn't say why. Can anyone guess? Why would you use unlink? The use of unlink is actually, it has several uses in the DL-malloc. The use that we will be speaking of specifically is the use of joining two adjacent buffers into one larger chunk that can be used for many more things. So you call free, your buffer is now freed and has all the nifty little management stuff involved. But then unlink, or it checks to see, hey, is this previous buffer in use? And it looks at what? It looks at that first 4 bytes. What's that? Exactly. It looks at that first 4 bytes just before your buffer. Is it even or odd? So, it's even. What would we do? Would we call on link or not? Yes. I heard the answer. Yes. You call it. Why? Because, well, the 1 isn't there. It's even. It means 0, which means false. The guy before me is not in use. However, notice that this buffer, the deciding factor of whether or not I call on link is up to me, because I just overflowed the guy before him. Does that make sense? But the devil is in the details. Do pay close attention. Ooh, that really didn't show up very well on the projector. Maybe with a laser pointer I can highlight it. How's that sound? So an in-use memory buffer. I told you that we'd go over this again. I stole this from Once Upon a Free. I have to give them credit because they did all this ASCII art. I modified it a little bit so it's adapted. So we've got the chunk. Starts here. Previous size, 32 bits long. Of course, if it's even or odd, means something. I'm sorry. This is before our chunk. I didn't adapt it very well, actually. I should have moved this down. This is a little confusing. I apologize. Here's where our data starts. The first 4 bytes is the size, and that's OR, bitwise OR, of previous in use. Then we have our memory. Then we have a next chunk. And again, that should be down lower. This last 32-bit integer, what does it really say? What's it mean? Previous size. Well, that's this up here. I'm sorry, this size right here minus the previous in use. So we're good. Yuck. An unused memory buffer, somebody who's been sent for deletion, so to speak, if you're into Tron, has also, just before our buffer, we have a previous size. Then we have the size of our buffer. Then our forward link, 32-bit buffer, and we'll see, or a 32-bit integer, a pointer. We'll see this in real data in a little bit. And a back pointer. Then we see the old memory, and again, we see the previous size. So, we've been lost. We got a map. Okay, we kind of got an idea where we're going, right? Okay, don't show your hands. Just agree. Good. So when onLink is called, back and forward, as I'll call them, obviously it's BIC and FID, but they are used to determine what bytes to overwrite in memory. Because in the end, that's what this is all about. It's not about, ooh, let's make this point to some other part of the linked list. No. We want to overwrite bytes. Is that not why we're here? Yeah. Why is that? Well, because if I overwrite the right bytes, I can tell the instruction pointer where to go. And yes, that has the same meaning as when I tell you where to go. It goes to hell in a handbasket. Or, as a hacker thinks, it goes into my code where it should be. So this happens whether you're collapsing backwards, so you're freeing, you're freeing this buffer and collapsing backwards, or you're freeing and collapsing forwards. Unlink is called both times. Both ways are exploitable in some operating systems or some implementations. So now we got 2 hands, we got a map. Let's take some real examples here. 804.96C4. What type of operating system am I talking about? Somebody yell it out. What's very common with an 804? Ed, you know. No? Yeah, sure. You're just being hard. It's Linux. POSIX, Unix, you name it, they probably have an 804 or something in there. 804.96C4, this is actually Linux. And 804 AOE8. Oh, wait, no. Those don't look right, right? Why don't they look right? Because that's not typically where a heap lives. In fact, in our test program that we will get to in a minute, AOE8 is the address of a GOT entry. Somebody yell out what GOT means? Global Offset Table, thank you very much. Global Offset Table, how is it used? For exploits. Yes, I like this guy. Okay, by design, the GOT table is a place where relocated parts of code that you didn't have to write because they're in a shared library are placed when you start a program. So how many of you have written a program that calls a library? A lot of you. Why? Because it's just so doggone easy. Why do it again? So, the loader for an operating system, and in this case Linux, says, I need the SSL library. I'm going to load it up here. And because we're a PLT GOT type thing, we're going to stick the beginning address for this function in the global offset table. Meanwhile, I call some SSL command. Well, let's just say printf. People know printf. So I call printf, and I'm not really calling printf. Not right away. What I'm really doing, my code makes call to the PLT. Who can yell it out? Yeah. Procedure linkage table. Thank you very much. We make a call into this special area at the beginning of our program called the procedure linkage table. It then jumps to wherever your SSL library or your printf function really live. It's really easy. The loader has to just keep track of a small area, and it's called relocation. Beautiful thing, helps us to reuse code. Also a beautiful thing because if we can overwrite 4 bytes, we have a great place to start. At the bottom, you see an example heap buffer overflow for DL malloc. We start off with hexadecimal representation of an address in memory. Wait a minute, that looks kind of weird, doesn't it? But trust me, this is how it looks like. We are on a least significant bit first operating system. Who came up with that? I don't know. But the idea is, instead of 804.96C4, we're going to start out with the C4 first, because it's just cooler for some reason. C4, 96, 04, and not just 8, of course, it's 08. Then we have another address placed here. What do you think these are going to end up being when we hit the free unlink mechanism? Pointers. Forward and backwards pointers, specifically. So we provide forward and backward pointers, D times 92, and I chose D for specific reasons, but basically it could be anything. Then I chose also to use a -4. The reason is unlink doesn't care. What it cares about is that it is even, and it has a couple other checklisty things that -4 is just beautiful for. So I use it twice. I use it here, and then I need a 4-byte pad for this particular exploit. So I use pad 0. Hey, it works. And then I put another -4 because just before the next buffer comes what? Its length. And again, unlink doesn't care what it is. So I'm going to use -4 again. -4 means what? Is -4 odd or even? Okay, not bitwise. -4 is even. If you drop the negative, it's an even number. You see, you can tell it's an even number because of the C. Can you figure that out? Just kidding. So yes, it's an even number, meaning that my buffer it's not allocated. I'll tell you why in a little bit. And then I stick the same two numbers afterwards. What do you think I'm doing? Why am I bothering to do this upfront stuff right here? Well, because I'm trying to make it so that if they free the second buffer, I win. If they free my buffer, I still win. So we have a map, we have two hands, we have a flashlight. So we've just set up memory space to make my buffer, which is in use, look like it's unused, at least for most intents and purposes. And we mentioned the GOT. And GOT is so beautiful, and it is read-write, so we like it. There are a few gotchas. Unlink doesn't just do the overwriting that we want it to do. Okay? Unlink does two things. It does one direction, pointing to a new place, but it also has the real problem of going the other direction as well. So when we unlink where you've placed your shellcode, the 8th byte through the 12th byte are going to get clobbered. Yes, for you elitists, it's 7 through 11. It's going to get clobbered. Can't help it. Sorry. This is kind of how it works. So we start out with a couple opcodes in our shellcode. If you're shellcoding, you're probably doing opcodes anyway. Except, of course, if you're using that HD Moore guy's tool, who I love. He's really awesome. Metasploit. Because Metasploit's just so easy. So we do our MSF payload and dump that to whatever storage facility, a file or whatever. And we then have to precede the payload from Metasploit with some of our own bytes. We stick in an EB, which is a jump to a single byte offset, which is important because we don't want to throw any zeros into this number. 1 byte. So we jump 0x E is the length. Including the opcode, it actually ends up being 0x10, or 10, sorry. We'll see this. I'm trying to explain it now because in a minute you're going to see exactly this. We then, I see it right there. EB, 0E, AA. We use A's just because they're easy. They also provide decent NOP codes if you have any left over. Notice I'm not just sticking in 8 A's here because 8's really what's going to get clobbered. I wanted to show you a little bit more representatively of what it's of the structures involved here. So I used A's, or 3 sets of A's. We could do this shorter, but there we are. Now here's where the gotcha comes. And yes, I realize if you want to get up and walk out, that's okay. I'll forgive you. They fixed this in glibc 2.5. In fact, I think I've seen it in 2.35. By somebody very intelligent adjusted the macro so that it says, just before we do this, hey guy to my left, are you pointing at me? Okay, good. Got him, all right? Good, we're set. Now we can unlink. I was hoping that by the time we got here, I would have a solution to this problem. Buddy of mine, Chris Eagle, maybe you've heard of him. Rumor has it, Chris has a way around it. We're going to talk after the con. After he's no longer my enemy and we're friends again, we're going to chat. So I wrote a little vulnerable program. Actually, it's a toy, not just for this presentation. So instead of just the very bare minimum of what we need, I started out and made a 5 heap buffer program. And I freed them in kind of a funky way. So take a look. Can you guys see this? I'm sorry, this font doesn't show up very well on the projectors here. I'm not hearing any complaining, so I'm going to go on. So hackme.c starts out just with the typical include stuff, nothing real special, standard lib, standard IO strings. Then we have a main function. Very simple program, actually. A main function, we set aside array of 5 character pointers to, character pointers. Yeah, I know. You guys are thinking, wait a minute. A buffer, or an array, kind of makes it so I don't have to use pointers, right? And pointers mean I don't have to use an array. But actually, we are storing the pointers themselves. So that's why they're 5. We also have a loop counter. And we loop 0 to 5. So 0, 1, 2, 3, 4. Okay, no, not 5. And we create some heap buffers using the call to calloc, or calloc. You've got malloc, you've got calloc, you've got several others that they all do different things. Calloc is intended to provide multiple buffers in a row with one call. And it zeroes them out for those of you who really care. Then we do a get s into each buffer, starting at 4 and going down to 0, just to throw in an extra kink. Let us play around a little bit. And then we have 2 loops here that print out the contents and free our buffers. Notice I'm stepping by 2, so I'm doing the even ones first and the odd ones second. Y'all with me still? I wanted to create a tool that could provide more than just a demonstration for this for this talk, but you can take home with you, you can play with it, and have fun and learn on your own and not have to rewrite your own program. I hate writing test programs. They're really annoying. It's like, I just want to do it. So can you give me something? Who read the Erickson book, Hacking the Art of Exploitation? Excellent book. I love it. In fact, I like it better, and don't get me wrong, I like it better than Shellcoder's Handbook. And don't throw eggs. Shellcoders is great. Erickson just really understood how to say, these guys need some examples, they need some hands-on, and they needed a very explicit teaching of what's going on. And he did an exceptional job. The guys who did Shellcoders are awesome. Some of them are my friends. I'm not picking on them. They write more depth. But Erickson did awesome with his examples. And I keep turning that off. So hackme details. We compile this down on a Linux system using GCC. This tells you exactly what I did. We get a warning. The getS function is dangerous and should not be used. Well, then it should be pulled from the library, you idiot. So I get a warning. Well, why would a developer ignore a warning? So then I use obsdump, which is a very cool binary manipulation, a binary analysis tool for ELF binaries specifically, but they do Windows too. Obsdump, using the R command, gives me the global offset table. I take a look here. Looks like the free function. Its location is stored in 804.96C4. Notice I didn't say it's going to be loaded at 804.96C4. Its pointer will be stored there. This is on your CD for Defcon, so don't worry if you can't see all this. I'm going to tell you what you need to see. A clean heap memory allocation of our program, mind you, not just some ethereal thing. Here is the 32-bit integer that marks the beginning of our first buffer. And if you can read it, it says 00000071. You hop down a little bit, and if you can see it, it also says, oh, right here, 00000071. That's our second buffer. How many bytes between this and that? I'll take hex if you don't want to do the conversion in your head. I know some of you are probably just turn that function off while you're here. Yes, 70 hex. Pop down here a little bit, see the same thing. And a couple more. I only had so much room. So 71 means 70 hex, or that with previous in use of 1. 70 actually converts, if you pop up kcalc, if you're using KDE like I do, it converts to 112. Wow. Everybody over here, look over here. This projector's better. I like it. I can read it. So I wrote this little exploit. Simple piece. It's in what language? Yeah, it's my latest love. Python. Import the OS module, import struct. I put in some shell code. 10-byte shell code. Anybody? Is that not slick? Okay, no, I really, it's a lot longer. I chopped it. I create a variable called @ that says this is where I want to overwrite to, this is what I want to change it to. I want to point here. And that's where my shellcode ends up. I then create @addy, which just converts this from a Python number into an actual byte. And I do the same thing to 2. Then I open my program, shove in a whole bunch of crap, and I get a shell on the other, or I get actually a listener on the other end. The most important part here, though, is you'll see I'm writing to one buffer here and another buffer there. That's just fluff. But then I write to the important one. I've selected one to be my buffer overflow. So I start out with an address that doesn't, no, wait a minute here. This is the shellcode. Forgive me. We start out with the jump over the crap that gets nailed. We then do our shellcode, and we terminate it with a carriage return. We write the next buffer, and then I selected the last one to be our buffer overflow. So we start out with, this is an example that you should have on your CD. It only focuses on collapsing in one direction. I've written several, they're all there. Okay, thanks. So we start out with our buffer, we do our number 4, -4, -4, and then we stick our addresses. Flush it, and we're good. This is what the stack looks like before we free. I'm sorry, the heap. So we filled up one section of heap with hex 45, which is an E. We have our number -4. We have our pad 0. This converts to pad 0 in ASCII. -4. Our number -12. That's because you go one direction, you're going to be offset by 12 bytes because it's not just the start of the next heap that you're talking about. It's an offset from the heap. Pointer to shellcode comes next. And right here, we're about to clobber that spot, and our shellcode starts there. Notice, got entry 804.834E. So this is where the, I forget what I grabbed here, the free. This is where free lives in virtual memory space. After free, we still have pointer to shellcode, still have some -4s, other stuff. You'll notice this used to be pad 0, it's now an address. Then started our shellcode, which jumps over that crud, a couple NOP codes, and our shellcode. Next call to free is going to be sent to 804 AOE8. And if you look up here, 804 AOE0, 8 is halfway through. It's going to point to right there. So I was going to demo it. I'm thankful that I had the slides that show what the demo was going to be, basically. Here's my Python, interactive Python, the hacking tool of champions. And netcat to port 4444. Thank you, HG. I type the ID, or I type ID, and hey, the program ID runs on the other box. Demo, not going to get to it, sorry, I got 2 minutes. I was going to demo, which still makes me stupid. Here's the bad news, I talked about it already. Somebody very intelligent said, hey, if these guys aren't pointing at me, bomb, corrupted double linked list. So what do we have left? Well, we've already talked about them a bit. Variable modification, end of string termination overwrite, or be creative. First of all, heap management is a complex thing. There are many aspects to it. We've only started to scratch the surface. There's more out there. Creativity is how we first discovered how to leverage buffer overflows. It's about getting something and then leveraging it. Pen testers, what do you do when you nail a box? You say, woohoo, call the client. No, you pivot. You then leverage what you have. A couple resources that don't show up at all. They are on the CD. You should click them from there or print them off. Special thanks to my creator, my family, to Intel Guardians, who are dear friends of mine, Ken Shoto, for giving me an opportunity to get a start, and last place, some of my closest friends and my team. Some graffiti, because graffiti's cool. Bug, Ringwraith, Menace, Jewel. Thank you very much, guys. Some of this stuff was stolen. Need to give credit, otherwise I get sued. Some people actually do know who I am. Thank you very much. It's been a great crowd. I enjoyed it.